So it's a pleasure to introduce our speaker today, Ulrich Bunke from Universitat Regensburg. And his title is that one you see there, Coarse, Homotopy Theory and K-Theory. Please, Uli, go ahead.
Yeah, thank you, Willy. I'm very happy to be able to give this talk here in this seminar. It's about a joint project or a central part of a joint project with Alexander Engel, who is now junior professor in Greifswald. And for the start, let me just come to the central statement I want to motivate and explain. So fix a countable group. So G always will be a countable group, and fix a C star category, yeah, with a G action. And I will assume that this category is sufficiently additive. And some of the main example you should have in mind is the category of Hilbert modules over a GC star algebra with compact operators isomorphism. So this is a basic example of a C star category, which satisfies all assumptions I need. And then the main statement I want to motivate and explain is the following. So there is a construction of an equivalent K-homology functor. So the notation will be Kx, so the coarse K-homology functor, with coefficients in the C star category, which goes from the category of G-bonological coarse spaces to the category of spectra. And one of the goals of this talk is to motivate what is this category and why this category. And of course, a little bit about how we construct such a functor. And just for completeness, this functor has some additional properties beyond being a coarse homology theory. So it's continuous, strongly additive, and admits transfers. I'm not able to explain these adjectives here in this talk, but just remember there are some additional properties, some adjectives, and we will revisit them in some statements later. So this construction allows to apply some general results from coarse homotopy theory, which are not specifically proven for K-theory, but for arbitrary coarse homology theories, to the special case of coarse K-homology. Yeah, and on the next two slides, I want to explain two of such results, which can be specialized to coarse K-homology. Yeah. But maybe first, let me justify the term K-homology, so why this functor can be called K-homology. So one justification is if we specialize the coefficients to just the category of Hilbert spaces and compact operators, and if we apply it to proper metric spaces with proper isometric G action, so these are examples, objects in this category in particular, then we recover the classical version of our result. Our K-theory is the same as the classical coarse K-homology, defined by, I think, John Rowe in the non-equivalent case, and by many people, considered by many people in the equivalent case. So another justification to call it K-homology is that if one restricts it to the orbit category, so if one considers the underlying equivalent homology theory in the sense of equivalent topology, and so the right way to restrict to orbit category is, okay, we look at the G set, G mod H, the orbit, equip it with a minimal core structure and a maximal bonology. So I will explain later what this means. And tensorize the thing with G, with canonical structures. Then the result will be the K-theory of the reduced cross product of the C star category with the fixed point group H of the orbit. So this is what you expect from an equivalent homology theory with coefficients in C. Equivalent K-theory with coefficients in C in the sense of equivalent topology. So I will come back later to this part. But now let me explain two results from general coarse homotopy theory, and how they specialize to coarse K-theory. So the first is about the coarse assembly map. So here G is a trivial group. So this is in a non-equivalent case. And So the general theorem is if E is any coarse homology theory, which is in addition strong. So strong is one of these additional properties listed in the previous slide. And the bonological coarse space has finite asymptotic dimension, then the coarse assembly map here is an equivalence. So let me explain what the symbols in this equation mean, because it's maybe not the coarse assembly map, I mean, not right the one you may know. So for us, if we fix a coarse homology theory, in our sense, we can always make a locally finite homology theory out of this using the cone construction. So if we precompose with a cone, then we get a locally finite homology. I mean, more precisely, so this thing is defined on uniform bonological coarse spaces, so spaces which have a uniform structure in addition to the coarse and bonological structure. But we can apply this such a thing to for instance, the finite dimensional simplicial complex with canonical structure. So the canonical metric, canonical bonology, metric bonology, metric uniform structure, uniform metric coarse structure. And then the value of this composition is the locally finite homology of the simplicial complex. In the generalized cohomology theory, E evaluated on a point. So E evaluated on a point is a spectrum, and then we have a locally finite homology of K with coefficients in the spectrum, and the sigma is just a degree shift by one. So this is really like a locally finite homology theory in ordinary topology. And the symbol P is then the coarsification. So the coarse assembly map in general goes from the coarsification of a locally finite homology theory to a coarse homology theory, and the same is here. So this is a coarsification, and this is defined as follows. So we take our bonological coarse space, and we form the Rips complex. So the Rips complex is, I mean, you can think of as finitely supported probability measures which have U-controlled support. So U is in coarse entourage of X. And so this is a simplicial complex. And so it has canonical structures. And so we can apply this locally finite homology theory to it. And then we take the co-limit over bigger and bigger coarse entourages. So this is the coarsification of the locally finite homology theory. And note that if X has bounded geometry, this is if and only if all the dimensions of these Rips complexes are finite, then, I mean, this is really locally finite homology. But this evaluation is always defined. Yeah, we don't need bounded finite dimensionality for this Rips complex. But somehow we understand what this is precisely in the sense of ordinary topology in this case. Anyway, so this coarse assembly map is then a natural transformation between coarse homology theories. So this is some of the main points. So both functors, so this one and this one, are coarse homology theories, and we have a natural transformation between them. And this is induced from the forget control map or cone boundary map. So the cone is essentially the product of R with X with a particular coarse structure, and so which is smaller than some of the product coarse structure. And if we make it bigger to the product coarse structures, and this is somehow the forget control map. So this comes from the cone boundary. Okay, so this is our version of the coarse assembly map. And the argument for this theorem is an adaptation of the thesis of Nick Wright. So he proved the statement about coarse K homology, but this statement, I mean, one can just axiomatize this argument, and then one gets this statement here, which is not specific to K homology, but of course one can apply it to K homology. And if one applies it to K homology and specialize coefficients to the Hilbert spaces with compact operators and proper metric spaces, then one can identify this coarse assembly map with the usual coarse Baum-Kohn conjecture assembly map. So that means that so this theorem reproduces the coarse Baum-Kohn conjecture by a purely homotopy theoretic argument. So there's no analysis at all in this. But note that, I mean, in the case of K homology, by specific arguments specific to K homology, one knows has a much better result. So one has much weaker assumptions on X versus this two. For instance, if X embeds in a Hilbert space, and by U, we know that the coarse form conjecture holds, but the argument is specific to K homology, while our argument does not use anything about K homology, except that the coarse homology theory with some nice properties. Okay. The other example is an application to equivariant homotopy theory. So now we look at an equivariant coarse homology theory, E. And again, as said before, it induces an equivariant homology theory in the sense of ordinary topology by restricting to the orbit category. So here we again do the same thing. We take the orbit, equip it with a minimal coarse structure, maximal topology, cross with G, and then we have this functor from G orbits to G bonological coarse spaces, and we post-compose with E. So this gives this functor in the orbit category. And somehow in the background is Elmendorf's theorem. So for me, spectrum-valued equivalent coarse homology theories are the same as functors on the orbit categories values in spectra. And the correspondence is just by evaluating the homology theory to orbits, considered as a discrete G space. So this is an equivalence of categories, and so I can consider this EG as an equivalent homology theory. Okay, and then the statement proven with Engel, Kaspersky, and Winges is the following. So if E, this equivalent coarse homology theory, is in addition continuous, strongly additive, and admit transfers. So these are also adjectives which were on the first slide. So this equivalent coarse K homology functor has these additional properties. And if the group, the underlying coarse space of the group, has finite decomposition complexity, say for the family of finite subgroups, and if there exists a finite dimensional CW model for the classifying space of proper actions, then the so-called Davis-Luck assembly map, so it's here, is split injective. So here, this notation is so HG with EG here. This is just the equivalent homology theory is, determined by this spectral valued functor, evaluated on the space. And this Davis-Luck assembly map is just induced by the map from this classifying space to a point. So this is a kind of Novikov conjecture, and for this equivalent homology theory. And this is proven by an axiomatization of an argument by Günther, Teixeira, and Yu. So this has been proven for equivalent algebraic K theory, but again, the argument does not use anything specific, it only uses the axioms. So it's general theorem about all coarse homology theories satisfying some natural additional conditions. But it can be applied to our coarse K homology, say with coefficients in the Hilbert modules over A. And if we do so, then as we have seen before, so we get really the functor constructed by Davis-Luck. So the values of this functor on the orbit category is just the K theory of the C-star algebra, reduced product of the C-star algebra A with the stabilizer. So this is the functor, appearing in the paper of Davis-Luck. And actually, in this case, we also have the Kasparov assembly map with coefficients in A. And actually, this Davis-Luck assembly map here, which is homotopy theoretically defined, is equivalent to Kasparov's assembly. This has been shown in the thesis of Julian Kranz, a very nice thesis. And using the techniques I'm talking about in this talk, we also have an independent argument for this. So what we see here is that this general theorem here recovers the Novikov conjecture for G and with coefficients in it. But again, this argument is completely homotopy theoretic, and in the case of K theory, we have analytic arguments which prove it under much weaker conditions. Again, this embedding in the Hilbert space is sufficient for the Novikov conjecture. So this is not the optimal result, but on the other hand, this is a homotopy theoretic proof. There's somehow essentially no analysis in this, just by specialization. Okay, so these are two results from general coarse homotopy theory, which applies then to K-theory. And let me now come back to some of the main topic, namely to explain why we want to have such a coarse K homology. So first, let me review the classical construction of equivalent coarse K homology. So how is the classical definition? And then I want to explain how it's generalized. So classically, this equivalent coarse K homology is a functor which has values in Z-graded abelian groups. And it's defined, say, on proper metric spaces with isometric proper G action. So this is somewhat natural domain of definition. And the formula for the value on X is it's the K-theory of a row algebra, which depends on the choice of an H and phi. And so this phi is an absorbing representation. So it's a representation of the function, continuous function on X vanishing in infinity on a Hilbert space, on the bounded operators of a Hilbert space. So everything has a G action here, and this should be equivalent, and it should be absorbing, so it should be sufficiently big. So essentially every other choice is a direct summand in this thing. And this C star XH phi G is a row algebra. So it's generated by bounded operators on H, which are G invariant, locally compact, and have finite propagation. And these notions are defined using these representations. So this is the usual definition. And then, I mean, one has to show that, one has to show it's independent of the choice of this absorbing representation. And, I mean, by similar methods, one can show it's functorial for equivalent proper and controlled maps. So this additional properties, I mean, some of the justification to call it coarse K homology are, okay, it sends coarse equivalences to isomorphisms, of course. It has excision, so Meyer-Vittori sequences for invariant coarsely excited decompositions of the space. And nice property, which is, so it annihilates flash spaces. So in particular, it annihilates products with array. So if you take any space, proper metric space, and cross it with array, then the value of such a theory is 0. Okay, so now let me come to the motivation why we want to extend to this bonologically coarse spaces. So first of all, note that the metric on X defines a bonology, namely the bonology of metrically bounded subsets. So as a way to talk, we can talk about bounded subsets in a metric space. And so bounded subsets, I mean, it's a subset of the power set which has certain closure properties, which should be clear. And this bonology goes into the definition of the row algebra by the notion of local compactness. So in order to say local, we use bounded sets, essentially. And also it goes into the definition of properness of maps, in the sense that I require that pre-images of bounded sets are bounded. And so it goes these two things. But now what I want to do is I want to consider bigger bonologies, which would be an independent datum added to X in the coarse structure, in the metric or the coarse structure. And then there is, so if I do this, then my notation will be XDB. So the first index is always the coarse structure, it still comes from the metric. And the bonology is now some maybe bigger bonology, maybe not some unbounded metric. So some bonology. And this bonology can be used in the same way as I use the metric bonology to modify the definition of the row algebra. So that I can define a row algebra with this bigger bonology. So then somehow this local compactness condition becomes stronger because I have more bounded sets. And somehow also the functoriality, somehow the condition of properness depends now on the choice of the bonologies. So, but then otherwise, I mean, I do the same definition and then I can define this K homology groups. Okay, so why do I want to do this? Why do I want to consider more general bonologies? So let me give just one example. So if you have a complete Riemannian spin proper G manifold, then we have a coarse index. So essentially this K-homology is designed to capture the index of Dirac operators. Yeah. So we have a coarse index of a Dirac operator which lives in degree dimension of X. Now I can, on such a manifold, I can define a new bonology. Namely, I call them subset bounded if, say, the scalar curvature on this subset is uniformly positive, maybe except a compact subset. Yeah? So, and now it turns out that somehow this coarse index of a Dirac operator is essentially localized away the set where the scalar curvature is positive. So this has been observed by John Rowe. And so we can define a refined coarse index, which is now in this K-homology group, which takes the bonology determined by the scalar curvature into account. So why is this good? So, I mean, assume that the scalar curvature is uniformly positive outside of a compact subset. Yeah, then the Dirac operator is Fredholm. And the bonology, of course, is everything. Yeah, the bonology is the maximal bonology. All subsets are bounded. Okay, but in this case, the Dirac operator is Fredholm, but this Fredholm index cannot be recovered from the coarse index. Yeah, so some of the coarse index loses the information about the Fredholm index, but it can be recovered from the refined index. How? Assume that G is trivial for simplicity. Yeah, I mean, look, the map which sends X to a point, it's now proper. It's obviously controlled, but it's now proper because all subsets of X are bounded. Yeah, and so by functoriality, I can just push forward this refined index to a point, and then I get, I mean, the K-series class. Okay, maybe this point is of course wrong, but I get a K-series class on a point, which is, yeah, the Fredholm index of the Dirac operator. So this is, I mean, so I can just get the Fredholm index from the coarse index, from the refined coarse index by applying, yeah, functionality. So that's somehow the application. Okay, the next thing is I want to motivate why we want to consider more general coarse structures, maybe which do not come from a metric. So note that the metric defines so-called metric entourages. So entourages are subsets of X times X.
Sorry, Ulrich.
Yeah.
I have a question.
Yes.
On the previous slide, when you define this new bonology,
yes.
When you say, you know, scalar curvature is positive, but to define the bonology, do you really need a positivity here?
No, I mean, this is just an example. So, I mean,
no, I mean, yes, to define the index, yes, you need this positivity so that you, but just for the bonology, you can define, for example, what if I just pick scalar curvature lower bound by some negative number? Would that work too?
Yeah, but then I don't have this.
Yeah, you don't have this index, yes.
Yeah, no, I mean, I want to define the bonology such that I get a refined index. This is the idea.
Okay.
So that's the goal. Of course, I can take any bonology which is bigger than the metric one, essentially, is good.
Hmm.
There is some compatibility with the coarse structure, which I will explain later. But you will see other examples of non-metric bonologies soon. So we have these metric entourages, yeah, so just the neighborhoods of the diagonal, yeah, given by the metric. And so these generate a so-called G-coarse structure on X. Yeah, and this coarse structure, again, it goes into the final propagation condition when we define the Rho eigenvalue. Yeah, there somehow that can be formulated in terms of the coarse structure. And the coarse structure, of course, also goes into the controlledness condition for maps. But again, everything can be formulated in terms of coarse structure, so we can allow more general coarse structures which do not necessarily come from a metric. So note that a metric coarse structure is always generated by countable sets of coarse entourages. Yeah, it's just enough to take these URs for the integers, so they generate the metric coarse structure. But I will explain an example of a coarse, a natural example of a coarse structure which is not countably generated in general, yeah, which we also want to learn. So, but maybe let's start with a simple example. So, for instance, there was this orbit with a minimal coarse structure, so the discrete coarse structure, all subsets of the diagonal. This is, I mean, in a strong sense, it's not metric because, I mean, of course, you can work with quasi-metrics where you allow infinite distances, then that would be good. Yeah, but in a precise sense, it's not a metric coarse structure, it's a minimal one. And also here you see the maximal bonology, which is definitely not determined by even the quasi-metric. Yeah, so here we use the freedom to use, I mean, to have bonologies and coarse structures can be chosen more or less independently. But I mean, the more interesting is, say, the continuously controlled coarse structure. So let's take a Hausdorff space and assume it's contained in a bigger space, which I call X bar. So I'm thinking some sort of compactification or partial compactification. And somehow the complement of X in X bar, I will denote by dx. So I think this is something of some boundary. And then, I mean, yeah, we call an entourage continuously controlled if the intersection of the closure of this entourage with the boundary is contained in the boundary, in the diagonal. So these entourages become very thin at infinity. This is the idea. Note that we also have a bonology here, so we call a subset bounded if the intersection does not intersect infinity. So we have both structures naturally given by this inclusion. And in general, these continuously controlled structures are not generated by countably many entourages. Yeah? So, okay, anyway. So now I think I have motivated why we consider this category of G bonological coarse spaces. So what are the objects? These are just G sets with a G coarse structure and a compatible bonology. So G coarse structure is a coarse structure, I mean, which is somehow invariant by G, with the additional property that there are sufficiently many G invariant entourages. So this reflects isometric actions. So I want say something like isometric action. So here I want that every entourage is contained in an invariant entourage. So this is the meaning of this. And this, I mean, G bonology, of course, is a G invariant bonology. And compatible means if I thicken a bounded subset by a coarse entourage, then I want it to be again bounded. Yeah, so this is a compatibility between the bonology and the coarse structure. Yeah, and morphisms are just equivalent maps which are proper. So pre-images of bounded subsets are bounded and controlled, meaning images of entourages are entourages. So this is our category. And somehow the slogan is now coarse homology series should be defined somehow in this category. Yeah. So it contains proper matrix spaces, but somehow it contains also the other examples one wants to consider. Okay, there's the last point. Classical coarse homology series usually have values in Z-graded abelian groups. And note that this is not sufficient to study assembly maps. So if we, for instance, if we consider this functor on the orbit category from some previous slide, but only remember the homotopy groups of the values, this is not enough to determine an equivalent homology theorem. Yeah, by Elmendorf theorem, we really need EG as a spectrum valued functor. Yeah? If we forget the spectrum valued functor, then it's not enough. But now the problem is that constructing spectrum valued functors is much more complicated than constructing group valued functors. So for instance, I mean, in the usual construction of course, in the classical construction of coarse K homology, yeah, I mean, for instance, in order to show it's well defined, we have to, we have different choices of these representations and we do some homotopies. Yeah, and all this is difficult to work with by spectrum valued functors. So I will explain how we solve this problem in a minute. But also say spectrum valued functors are good in some sense because then they're very useful if one wants to do investigations by universal properties. So somehow this is much more complicated to formulate universal properties using these group value functions. One can do this, but it's just more involved. Okay, anyway, so now we can come to the definition. So what is a spectrum valued equivalent coarse homology theory? It's just a functor from this category I just explained to spectra, and it has the following four properties. So it should send, so it's coarsely invariant, so it should send coarse equivalences to equivalences. This is some of the basic. Then it should be excisive, so it should be coarsely excisive decompositions to push-outs. It should annihilate these products with rays, so that means annihilates flasks, is the technical term is. And it has some force condition, which is very important. It's called U-continuous, and I will explain when I discuss the construction of the K-homology functor. I will explain what this means, yeah, because I will explain why this functor is U-continuous, and I will explain the definition. Okay, these are these four axioms. Okay, now let me, in the remainder of the talk, I just will explain how we define the classical definition to a spectrum valued coarse homology theory defined on this big category, and how we introduce coefficients. Actually, this is both coming in one thing. Okay, so let me start with the construction. So some of the basic idea is to work with controlled objects in the C-star category. Actually, this is, I mean, before we discussed topological K-theory, we discussed, I mean, we constructed such functors for algebraic K-theory, yeah, and some of this construction is very much modeled on the algebraic constructions. So it's very similar to what we have done in algebraic K-theory. So, okay, if one wants to straightforwardly extend the classical definition, then I mean, the first problem is that these, okay, the continuous functions vanishing at infinity on X is not really defined because there's no topology. Of course, one could work with the discrete topology if one wants to. This would be good. So our way out is, okay, let's work with projection valued measures. So this is enough to formulate the conditions we want to formulate. But more serious is that these representations have to be chosen. So there's some ambiguity to choose these representations. And this is, as I said before, very problematic if one wants to have spectrum level functoriality. So this is a problem. And even worse, I mean, in this generality, we do not have absorbing representations at all in general. So if the group, for instance, doesn't act properly, then this, we cannot have that. So the question is now how we can solve this problem. And the way out is, of course, okay, don't fix an absorbing representation, but just work with all such representations. So the idea is just work with the C-star category of all representations and somehow define morphisms between two representations in the same way we define the row algebra. So actually what we generalize here is a uniform row algebra to the C-star category. We don't stabilize. Okay, so let me, so the sum of the idea is now, okay, we have to construct the row category functor, which is a functor from demonologically coarse spaces to C-star categories. So this NU stands for possibly non-unitil. So we don't require unitil, and also we don't require that functors preserve units. So these are non-unitil C-star categories. And so the objects in the C-star category are these equivalent X-controlled objects in the coefficient category, and the morphisms are row morphisms. So let me give a quick explanation what these objects are. So an object in this category is a triple, where C is just an object in the coefficient category. Rho is a co-cycle of multiplier morphisms on this object, which implement G invariance. And mu is a measure defined on the power set of X, which is G invariant, finitely additive, effective. So effective means every value has an image. So we have a lot of projections, and all these projections should have images. It should be locally finite, locally finite. And the morphisms are generated by equivalent controlled propagation multiplier morphisms between the objects. Yeah, and this controlled condition uses the measure, and equivariance uses the cocycle. Okay, so maybe yeah, and okay, on morphisms, if I have a map between monological coarse spaces, then I just push forward the measure. Yeah, so on objects, so the functor sends this triple to this triple, where I just push forward the measure, and it does nothing on morphisms. So this is a very short explanation what this category is. And maybe I skip some more. So I wanted to tell some more details, but so on the slides you can read them, but I think I will not explain them here for reason of time. But I want to explain what are the properties of this functor. So somehow I want to group these properties as follows. So there are some properties which are used to verify the axioms of coarse homology theory, and there are other properties which are used to verify the additional properties and do calculations. So the basic properties are, it's causally invariant, so meaning this functor sends coarse equivalences to unitary equivalences between these star categories. It's excisive in the sense that it sends coarsely excisive decompositions to excisive squares in C-star categories. So what does this mean? So what is an excisive square in C-star categories? It's the square of C-star categories here, yeah, where A and B is an ideal inclusion and E to F is also an ideal inclusion, and the map here between the quotients should be unitary equivalence. So this is what I mean, called an excisive square. And if I apply the functor V, this row category functor to such a square, then I mean it sends this thing to an ideal in this, and so it sends, you get this excisive square. So here this brackets mean I don't really consider a fixed space, but I consider the family of all thickenings, coarse thickenings of the space, and somehow I extend this functor to such families by forming co-limits. Otherwise, I wouldn't get ideals. Yeah, so this is very natural. So this excision condition in coarse homotopy is usually formulated in terms of a subset and a complementary family of a subset in all its thickenings. Okay, so this is excisive. It preserves fleskness. So it sends a flesk chronological coarse space to a category which is flesk. This means this category has an endofunctor S, such that if I add the identity, it's unitary equivalent to S. Yeah, so these are categories which allow an Eilenberg-Schwindel. So, yeah, so this is a flesk C-star category. And it's U continuous. Now I can explain what it means. So I can get the value of the functor on X as a co-limit over the values evaluated on these spaces XU. So these are the same sets, the same monologies, but here the coarse structure is just generated by a single entourage U. Yeah, and this is what I mean by U continuous. So essentially, everything can be calculated in terms. So this reflects somehow the idea that every generator of morphisms in this category has an entourage which controls it. So that's why we have this. Okay, additional properties are it's locally finite. So this comes from the local finiteness of the measure. So the value of this functor is the co-limit over the values on locally finite subsets. Yeah, and the subset is locally finite. Of course, here I work with G invariant locally finite subsets. So it's locally finite if the intersection with every bounded subset is finite. So this uses a bullet. And it sends, I mean, this is also, yeah, I will not say more, it sends some sort of co-products, these three unions to products of categories. So that's important to show this strong additivity. Okay, now in order to go further, I have to, I have to go to spectra, and for this, I will use a spectrum valued functor, K-series functor for C-star category. So I want to use this functor. And so this functor is provided essentially by Michael Joachim.
So
I think he did it. Yeah.
Sorry, are you referring to this work of Joachim where he associates an algebra functorially to a C-star category and then take the K-theory of that algebra?
Yes, so in this paper he does this.
Yeah, okay.
Where he somehow corrects this mistake in Davis-Luck. This is this paper where he constructs the Davis-Luck functor correctly. Yeah. Actually, I will come, I mean, there are more details of this. So, I mean, first of all, if I have such a functor, then, I mean, our definition is just the composition. Yeah, I compose the row category functor with the K-series functor, and this is our coarse homology. Yeah, and so let me say a little bit more how we get this functor. Of course, this construction is essentially due to Michael Joachim. So he observed that we have an adjunction between C-star algebras and C-star categories. So he did, I mean, somehow I say essentially because he did everything in the unital case. So here we have non-unital category. But anyway, this is more or less the same. So a C-star algebra can be considered as a C-star category with a single object. So there's just an inclusion of categories here. And this inclusion has a left adjoint, which I call AF. Yeah, so this sends every C-star category to a huge C-star algebra, essentially freely generated by the C-star category. Okay, we have this functor, and then we need a spectrum-valued K-series functor for C-star algebras. Okay, there is one in Michael Joachim, but nowadays, okay, we like infinity categories, and there's a very formal construction of a spectrum-valued KK-series by Land and Nikolaus. Yeah, which does not need any explicit models. So it's just as a Dwyer-Kahn localization of this category by KK equivalences. One gets formally such a functor. So nowadays it's not a problem to define such a thing. And then I mean this C-star category K-series is just a composition of those two. So in this way we get it. And now, again, I need some properties of this functor in order to show the axioms or verify the axiom of a coarse homology. So let me just list them. So, of course, this functor sends unitary equivalences between C-star categories to equivalences. It's not obvious from this definition. So one has to work a little bit, yeah, to show this. Because some of this AF, this does not really interact well with unitary equivalences. But essentially, this has been shown already by Michael. It sends excisive squares to push-out squares. Okay, this is essentially sort of exactness, yeah. So it sends exact sequences of C-star categories to fiber sequences, and from this we get this. It preserves filtered co-limits. So all the co-limits which appeared in the previous slides were all filtered. So these co-limits are preserved by the K-series. And it annihilates Flesk C-star categories. So, and with this, it's completely formal now. Yeah? Once one knows the property of the row category and these properties of the K-series functors, then it's clear that this thing is a coarse homology theory. And for the additional properties, we need certain Morita invariance statements about this K-series, and that it preserves arbitrary products of C-star categories. This is for this additivity. Yeah, and at the end, because I think these statements about the K-series functor are of some independent interest, let me, in the last slide, explain in some more detail what these statements mean. Yeah, so, okay, first of all, product preserving. So if you have any family of C-star categories, and then we have the following. So if every member of this family is additive, so actually, I mean, maybe here saying non-unital is maybe too much, because if I assume it's additive, then these categories are unital, yeah, an additive category. So additive means admits finite sums. In particular, it admits sums of, yeah, I mean, one element sums, and this, if one see what this means that in particular the objects have units. So if every member of the family has finite sums, then, I mean, there is a canonical morphism from the K-series of the product of the categories to the product of the K-series, and this is an equivalence. Yeah, so the proof is very similar. I mean, in the book of Wille de Jong, there is a proof. Say for stable C star algebras, yeah, you have also similar result and somehow, yeah. So in K0, it's not so complicated, and to prove it for K1, yeah, you have to make homotopies. Uniform. You have to make homotopies slow, and you can do it at the cost of going to matrices, and for this you use this additivity. So anyway, so this is true. And now I come to two Morita equivalent invariant statements. So I do not want to formulate the most general results because it would be too long. But so let me assume that I have a fully faithful functor. So this means that I have it's a functor which is a bijection on morphism sets. And assume that both C star categories are unital and both admit finite sum. So these assumptions here are only for simplicity. Otherwise, the statement would be a little bit more complicated. And then the theorem is that this K-series functor is Morita invariant, and this means if every object of D is a summand of an object of C, so every object here is a direct summand of an object here. Then the inclusion induces an equivalence. So a typical example here is, okay, consider the inclusion of finitely generated free Hilbert modules over A into finitely generated projective Hilbert modules over A. Yeah, for unitary A. So this is an example which satisfies this assumption. Yeah, and if you want, also you could include A into this. Yeah, this would also be a Morita equivalence. Yeah, but of course here A is not additive. So yeah, but then I would have to give us the different statement. Yeah, but also this inclusion induces an equivalence. Okay, so maybe you can.
There you just define the K-theory of a ring as the K-theory of a linear category as the K-theory of the station of a category, and then you have the theory.
The K-theory of A is a K-theory of A. The K-theory of A, so if I apply my definition of C star category K-theory to A viewed as a C star category, then I get the ordinary K-theory, C star algebra K-theory of A. So I don't go to Hilbert spaces. So this is not a formality. So again, so if I include A here, this is not the identity on the level of categories. So it's really a statement.
But so are you saying that this Joachim algebra of this category of Hilbert modules is Morita equivalent to A in the end?
No, I say that A is Morita equivalent to this category.
Okay.
This is what.
Okay. Okay.
Yeah. But so, what I used here is, I only wanted to state Morita equivalences for additive categories. And A is not additive, that's the point. Yeah, but there's a big, essentially, okay, A to B, so a morphism from C to D is a Morita equivalence if I make the finite sum completion, if this satisfies the assumption of the theorem, then that's the general definition of Morita equivalence for unity. Yeah, and there's also a version from the unit. Yeah, but this is.
So what I said is that, I'm thinking completely algebraically. Maybe there's some difference because we are in the system.
So that's completely algebraic. So this Morita invariance is a completely algebraic Morita invariance. There's no analysis.
Yes. So the category of free modules is the C. If C is the ring, the category of free modules is C plus.
Yes. So yes. So this.
That's what I meant.
A plus. Right. Yes. Okay, so but maybe more interesting because it's not algebraic is the weak Morita invariance. So again, we look at the fully faithful functor. Fully faithful functor, and again, as for simplicity, assume that the target is additive. And then I say, okay, if every morphism in D can be approximated by morphisms which factorize over finite sums of objects of C, then again, this inclusion is equivalence. And here, I mean, maybe it's complicated to parse, but I mean, somehow you should have in mind the following example. So we take a unitary algebra and just we consider the functor which sends these A into the Hilbert modules over A with compact operators. So this is a huge category, and this is a category with a single object. But of course, every compact operator here can be approximated by operators which factorize over finite sums of A. By definition, more or less. So, yeah, this is an equivalent. This is an example of a weak Morita equivalence, and so K-theory sends this thing to an equivalence. So this we have used in one of the calculations. Yeah, so somehow if we want to calculate the K-zero of this category, then it's the same as the K-zero of A. This has been used in some previous slide. Okay, so that's what I wanted to explain. Thank you very much.
Okay, thank you, Uli, very much. It's a very nice talk. I've already asked questions during the talk, so let me give the opportunity for someone else, if someone else has a question. Chat. So, well, while people are thinking, let me see if I grasp the basic idea. So you show that there are some properties of assembly maps that hold for any good coarse homotopy, coarse equivariant homology theory, by purely formal consequences of the actions.
Oh, let me come back. No, it's different. So maybe let's see. Let me come. Just want to go back to this page. So here, okay. No, the point is the following. So, I mean, okay, you have a functor on the orbit category, say this EG, and somehow, okay, if you want to apply methods of coarse homotopy theory, to say something about the Davis-Lucke. So, if you have such a functor, we can talk about the Davis-Lucke assembly. And yeah, just I mean, it's defined here. It just needs a functor. And now, if you want to apply coarse methods to such a functor, and I mean, the usual, some of the natural thing is, okay, we want to prove something about the assembly map for the family of finite subgroups. One can do something for other families, but somehow everything essentially at the end is reduced to this case. Yeah, then so as here. Then, I mean, what you ask is, can you extend? So if you start with this functor, then the question is, does it extend to a nice coarse homology theory? Yeah, so is there an E which gives this functor by this formula, which has these additional properties, continuous, strongly additive, and transverse, and then we can conclude. Yeah, so the idea is, okay, give me a functor, and then I have to construct for you an extension to a coarse homology theory. So essentially what I can say is all functors which have been considered so far, L theory, algebraic K theory, A theory, algebraic K theory for stable infinity categories, any such functor, we have found maybe not for L theory. So L theory I take back. Yeah, my colleague Christoph Winges is working on this. But for all the others, we have found a coarse homology theory which does the job. Yeah, and somehow the message of this talk is, okay, we can also do it for topological case theory, and somehow explain how we do it. So if we take any use, I mean, the topological coarse homology, the topological K homology introduced by Davis-Luc, then it extends to coarse homology theory, which has all the properties needed to apply such a theory. I mean, there are more theorems of this kind which I have to talk about, but they all apply to this.
Okay.
Yeah, and essentially all functors I know which have been considered, they also ordinary homology. Ordinary homology extends to coarse homology. Bordism, there are a lot of many examples.
Jonathan has a question, Jonathan Rosenberg.
Sure. So first of all, this was really beautiful talk, very interesting. And I saw your paper, but I didn't have the patience to read it all the way through. So I appreciate your explaining it. So while you're on this slide here, what does this assumption G canonical has FIN finite decomposition complexity really amount to when G is a discrete group? I want to make sure I'm parsing the theorem exactly.
Okay, so it's actually it's very complicated to verify finite decomposition complexity. So maybe assume that G is torsion free, then we can drop this. Then I mean, this is I mean, somehow. Let's assume G is torsion free. Then it's just finite decomposition complexity. And so, for instance, if you have finite asymptotic dimension, implies finite decomposition complexity. But it's somehow, for instance, I think the infinite product of sets, countable sum of sets, so countable sum of sets also has this finite decomposition complexity, but does not have finite asymptotic dimension. So it's but I mean, in the paper we have some. I mean, essentially, Daniel Kasprovsky is a specialist, at least in our group, who knows how to verify this or deduce this property from other properties. Yeah, so there are some. I mean, it's difficult to find examples which do not have finite asymptotic dimension and do have finite decomposition complexity, and they cannot. I mean, from my head, out of my head, say which they are, but they exist. But it's complicated to construct them. Usually, if you give me a group, then if I can verify this, then it also has finite decomposition complexity. But there are examples which,
A good class of example is like the linear groups, which have finite decomposition complexity, but many of them don't have like finite asymptotic dimension.
So, does anyone have any other question or comment? Okay, so my part, I think we are done. Sean, you are recording.
much for listening.
Why is all right.
Bye.
Bye.